Hi, long time no see. Welcome back to Dr. S's Random Math Lair. Today's video features problem 5 regarding Taylor series, a kind of convergent power series used to locally approximate a whole host of important differentiable functions. Generally, when we talk about the Taylor series expansion of a differentiable function, it is done about a given point in a neighborhood where the series converges, and for this reason the approximation is considered local. This topic is normally covered in an upper-level undergraduate course in advanced calculus, or can be extended to complex variable theory in a first-year graduate course in complex analysis. For all intents and purposes, this video will be based on a combination of advanced calculus and complex analysis. Some important historical background and information will also be presented. Here's the statement of problem 5. Prove Euler's formula, given by star, using local Taylor series of the complex exponential, cosine, and sine functions, about the point z0, equal to 0 in the complex plane C. Note that z is any complex number, and I is the imaginary unit, given by the square root of -1. Now we shall consider a bit of historical background behind the two mathematicians mentioned in this problem. We'll start with Euler first. Leonhard Euler was one of the most influential mathematicians of the 18th century. He was born in Basel, Switzerland, and studied at Basel University under Johann Bernoulli. At the time, the Bernoulli family was dominant in Swiss mathematical circles, so it was difficult for Euler to find a decent position or level of recognition in his hometown. For this reason, most of his academic life was spent in Russia and Germany, Prussia at the time, where he would eventually teach at the Imperial Russian Academy of Sciences and Berlin Academy. Later in life, Euler suffered blindness in one eye, but regardless, he remained sharp in his mental calculation skills and memory. Here are a few of his main contributions. Much of today's modern mathematical notation, such as f of x for a function f applied to the variable x, and the Greek capital sigma denoting a sum, were created or made popular by Euler. Euler used and developed power series in his studies and research in infinitesimal calculus and analysis. He contributed to analytical geometry and derived Euler's formula, which we will be proving in this video. He also proposed a solution to the 7 bridges of Königsberg problem. The city of Königsberg was situated on a river, which included 2 islands connected to each other and the mainland by 7 bridges. The problem asked if it were possible to follow a closed path that crossed each bridge exactly once, and return to the starting point. Euler showed that it is not possible, and this became one of the precursors for the field of mathematics known as graph theory. Now we shall discuss a bit about Taylor's background. Brook Taylor was born toward the end of the 17th century in Edmonton, England. Taylor attended St. John's College at Cambridge, where he studied law, mathematics, and philosophy. While earning degrees in law, in his mathematical studies, Taylor came up with a solution to the problem of the center of oscillation in 1708, although receiving harsh criticism from Johann Bernoulli. A few years later, he served as a Fellow of the Royal Society, and determined the movement of a vibrating string, based purely on mathematical and mechanical principles. Here are a few of Taylor's contributions. Taylor developed a new branch of higher mathematics, known as the calculus of finite differences, in his 1715 publication Methodus Incrementarum Directa et Inversa. He applied the ideas from this paper to the movement of a vibrating string. He also made early contributions to perspective art in his 1715 essay Linear Perspective, from a novel geometric and technical approach. Taylor invented the method of integration by parts, a fundamental part of integral calculus. Taylor's theorem and Taylor series expansion were another highly important contribution of his to modern mathematics. There's even an impact crater on the Moon named after him. Next, we shall consider some quick facts and review to solve problem 5. Before the end of the video, we will briefly discuss the history of an important concept in complex analysis, which will be useful in solving this problem as well. Here are a few important quick facts and review to solve problem 5. First, any function that can be written as a convergent power series in a neighborhood of each point in its domain, is called analytic. A complex function of one variable, or more, that is complex differentiable in a neighborhood of each point in its domain, is called holomorphic. In particular, a function holomorphic on the whole complex plane C, is called entire. We will define, and take a far more detailed look at complex differentiability in a future video, as we shall assume the complex functions in problem 5 are complex differentiable. A holomorphic function is infinitely differentiable, and locally equal to its Taylor series, and this is precisely the convergent power series representation of such a function. For the function f of z, where z is a complex number, its Taylor series about a point z0, in a neighborhood U of its domain D, is given by f of z equal to the sum from n equals 0 to infinity of a n times z minus z0, to the nth power. The Taylor coefficients a n are equal to the nth derivative of f evaluated at z0, over n factorial, for all non-negative integers n. Note that the 0th derivative of f evaluated at z0, is simply f evaluated at z0, and 0 factorial is 1. In particular, when z0 is 0, the above series is called a Maclaurin series. Let's solve problem 5. In star, let f of z equal e to the iz, that is, the exponential of iz, let g of z equal cosine z, and let h of z equal sine z. Note that the functions f, g, and h are entire, so star will hold for all z in the complex plane C. Certainly, these functions are holomorphic in a neighborhood of C, for instance an open disk of radius r, centered at z0, given by the modulus of z minus z0, being less than r. Here, we consider z0, equal to 0. So we are actually considering Maclaurin series. Recall that I is a complex number given as the square root of -1, I squared is -1, I cubed is I to the 4th power is 1, I to the 5th power is I, and so on and so forth. Computing a few derivatives of f at 0, we have f of 0 equal to 1, f prime at 0 equal to I, f double prime at 0 equal to -1, the third derivative of f at 0 equal to -I, the fourth derivative of f at 0 equal to 1, the fifth derivative of f at 0 equal to I, the sixth derivative of f at 0 equal to -1, and so on and so forth. Then the Taylor series about 0, for the exponential of iz, is f of z equal to 1 plus iz, minus z squared over 2 factorial, minus I times z cubed over 3 factorial, plus z to the 4th power over 4 factorial, plus I times z to the 5th power over 5 factorial, minus z to the 6th power over 6 factorial, and so on. We are not done yet, so let's continue to solve this problem next. Let's continue to solve problem 5. Now let's write the Taylor series of f of z about 0, again for reference. Recall that we let g of z be cosine z. Computing a few derivatives of g at 0, we have the following. So, the Taylor series for cosine z about 0, is g of z equal to 1 minus z squared over 2 factorial, plus z to the 4th power over 4 factorial, minus z to the 6th power over 6 factorial, and so on. Notice that these are all even powers, with alternating signs. H of z was sine z, and computing a few derivatives of h at 0, we have the following. Thus, the Taylor series for sine z about 0, is h of z equal to z minus z cubed over 3 factorial, plus z to the 5th power over 5 factorial, and so on. These are all odd powers, with alternating signs. From the Taylor series about 0, for f, g, and h, we easily see that f of z equals g of z, plus I times h of z. This proves star, or Euler's formula, as needed. Before we end this video, let's briefly look at some background and history behind holomorphic functions. From the definition of an analytic function, mentioned earlier, analytic functions are locally represented by convergent power series. The two main types of analytic functions are the real analytic functions and the complex analytic functions. Complex analytic functions are also called holomorphic. The theory of analytic functions originated in the 19th century, with contributions from Euler, Gauss, Cauchy, Riemann, Weierstrass, and many others. By the 20th century, this theory was extended to the complex domain, where it became known as complex analysis, or the theory of functions of a complex variable. The term holomorphic was coined by two of Cauchy's students, derived from the Greek holos, meaning entire, and morphe, meaning form or appearance. With the evolution of complex analysis, many important results came about. One of them was the Cauchy-Riemann equations, which state that if the function f of z equal to u of xy, plus I times v of xy, where u and v have continuous first partial derivatives with respect to x and y, is complex differentiable on a domain D of the complex plane, then the partial derivative of u with respect to x, equals the partial derivative of v with respect to y, and the partial derivative of u with respect to y, equals the negative of the partial derivative of v with respect to x. And conversely. Moreover, the complex derivative of f is f prime of z, equal to the sum of the partial derivative of u with respect to x, with I times the partial derivative of v with respect to x, which is also equal to the sum of the partial derivative of v with respect to y, with negative I times the partial derivative of u with respect to y. We will discuss more about this interesting result in a future video, so stay tuned. Don't forget to subscribe, if you liked this video.